Good morning to everyone. So now we will start today's session. That is the session number 10. Session number 10, which is offline. ATAL FDP program, hybrid microgrid, opportunity and challenges for renewable energy resources. I am Dr. Shivam, Assistant Professor of Electrical Engineering Department, NIT Kurukshetra. Heartily welcome Chief Guest of the day, Professor D.K. Jain sir. He is a professor in Department of Electrical Engineering, DCR, University of Science and Technology, Murthal, and coordinator of the ATAL FDP, Professor Ratna Dahiya, coordinator of a School of Renewable Energy and Efficiency, Professor in Electrical Engineering Department, NIT Kurukshetra, and the faculty members and participants of the event. The primary objective of the ATAL FDP is to provide a national forum to the faculty and research scholars to share the basic knowledge with an objectives of understanding the concepts, aspects of penetration of renewable energy sources, electric vehicles, and with the hybrid microgrid operation. Now I would like to address of today's session a speaker, Professor D.K. Jain sir. Currently, he is a professor in Electrical Engineering Department, DCR, University of Science and Technology, Murthal. He has done PhD, MTech and BSc from REC Kurukshetra in 1987, 1993 and 2001 respectively. He is the senior member of IEEE and life member of ISTE-IE. He was in Technology Advisory Group of Inerson India Limited, Mumbai, now Wind World India Limited, on wind energy conversion system and MF solar system for solar power generation. He has guided more than 10 PhD, and also he is guiding PhD supervisor. His student received POSCO award for PhD thesis work. He was given Outstanding Chapter Engineer Award by PECIS, Chapter of Delhi section, for his contribution of renewable energy system. He has been General Chair for Power India International Conference, sponsored by IEEE in 2012 and 2020, and Technical Chair for IEEE Conference of PESIS Delhi section. His areas of interest include electric power quality, integration of renewable energy sources, electric drives, and more on the microgrid. He has published more than 100 papers in national and international journals and conferences. So I would like to welcome sir for this session. Welcome, sir.
Yeah, thank you, Dr. Shivam, for the nice introduction. So I again welcome all of you. So today, you see, we have a very cold weather in this region, right? And no solar. And in this season, we have little wind, right? So here we will not be having in these days solar and wind, right? So we cannot just think of having, say, these resources available for us, right, during winter, most of the time. Okay, but does not matter. So today I'll be giving you a brief about how do we control voltage and frequency in our grids, right? And later on I'll come to the microgrid, how it is more pertinent or effective in case of microgrids. It becomes more useful to see, right? So I'll start with the working of a solar or a wind power station, right? And nowadays, you see, we are trying to have net zero by 2070, right? So there will be using most of the sources will be renewable in nature, right? And there will be a little firm power which is available nowadays. That is a coal or diesel, whatever it is, wherever it is, right? So the contribution of these resources will be little, right? And our solar or thermal or solar or wind or other resources, right, renewable resources, they have to act as a firm power, right, not intermittent, right, but as a firm power we have to have them. So that means they should behave in the same fashion as our thermal power stations do nowadays, right? So I'll start conversion with that only. What is the beauty in thermal power station? Means why it is called a firm power. Okay. What is there in the thermal power station or a nuclear power station, right, which makes him to work as a base load or a firm power station? Yes? Yeah? Yeah, what is there in thermal power station so that it can act as a base load power station? You're talking about ramp rate? Okay. So ramp rate is a constraint, of course, right? So generally, thermal power stations have a ramp rate of around 4% per minute. Right, so you cannot ramp so fast. See, if you see the Indian load pattern, right, daily load curve, you will find that there is a morning peak around say 6 to 8 or 7 to 9, and later on in the evening we have an evening peak, right, from 6 to 10, something like that. So you have a sharp peak, right? So you need sharp ramping in the morning as well as in the evening, right? We have ramping, but you see thermal power stations, they have slow ramp rates, right? Ramp up and ramp down, right? Say 4%. Nowadays, of course, they are going for 6%, but that is not sufficient for fast ramping, especially in the evening. I did not reproduce that curve, but if you see the net load here, right? In the evening, you have very fast. It looks like a duck. Our load looks like a duck, right? A sitting duck. We call it a notorious duck, right? So ramping is very difficult. So, of course, thermal power stations cannot ramp very fast, but till we have at least more than 55% load being served by the thermal power stations. So that is called minimum loading on the thermal power stations nowadays in India. So we cannot go below 55%, right? So what is there another thing which is there in thermal power stations which make it look like a firm, right? What is difference between the operation of a wind or solar power station and a thermal power station? Right. See, you know the configuration. Say, in case of a thermal power station, how do you control the voltage and frequency? Yes, that is AGC. Use automatic generation control there, right? You change the input, right? So as to ramp it up and down, right? So that is called AGC, automatic generation control, right? Can you do this in solar power station? Up, ramp up, down you can do, right? But up you cannot. But I will tell you how it can be done. My today's lecture will be how these solar and wind can act as a firm power, or like a thermal power station, right? As a firm power stations. right? So coming back, so one is AGC. You provide power output control, the frequency control, you mean to say, right, by changing the input to the set turbine, right? Next, how do you control the voltage in thermal power stations? Yes, changing the excitation. So that is voltage regulator we have, AVR. So we have AVR there. Automatic voltage regulator is there to vary the voltage, right? Or to control the voltage, in fact, right? By varying the excitation, we can change the output voltage, right? Do we have AVR in solar or wind? Wind, I'm talking about back-to-back connections through an inverter, right? Not directly connected. That has become obsolete nowadays. Say directly connected induction generators, right? So another version has come, right, with power electronics interface, but I'm talking about back-to-back. Say in case of wind, we have variable voltage, variable frequency generation, right? Then we say rectify this, make it a constant DC somehow, and then from DC to back to AC, so that we can synchronize it to the local grids, right? So in case of that is the configuration. So where is the voltage regulator here? Do we have separate voltage regulator like a thermal power station? Right, we don't have. So these two are called the heart, right? So we have to control the frequency and we have to control the voltage, right? And that are missing in conventional control of your wind or solar power stations, right? Or say variable generators for variable generators, right? So how to make it or how to introduce these into the operation of solar and wind power stations, right? Okay. So these are variable generators, right? And these are intermittent in nature, but these are not, these are predictable, right? We can predict very well. Day ahead also we can predict, but of course accuracy will be bit lesser, right? But we can very well predict and then bid also, right? So that nowadays we can do this. See, I had visited one wind power station in Jaisalmer in India, right? So there were so many machines, wind machines, right, of the size of say 800 kilowatt at the time, right? Say 10 years back, right? But that machine was connected back to back through an inverter to the local grid, right? So there were say so many small units, 800 kilowatt size units spread over a vast area, maybe hundreds of units, such units. And generally owner is not a single owner for the turbine, right? Single machine. They are the developers, right? And they install machines and operate the system, right? For the others people. So there will be so many owners of those machines of a wind farm. So that person becomes an aggregator, right? Say any company, Suzlon you must have heard about, right? Right. Likewise, Enercon was there at that time. So these are aggregators, developing wind farms for others and operating them, right? They have say power purchase agreements and all, something like that, right? Operating agreements, and they run the plants for others with some certain reliability, right? So once we aggregate the machines, so their variability becomes lesser. If you aggregate, so single machine will have a lot of variations in the power output, but if you aggregate, it becomes a smooth curve, right? That means you can rely on that, and it can act as a firm power, or you can bid it, right? So that is why, say now in India we have renewable energy management centers in major districts where we have a lot of renewables, like in Gujarat we have, Rajasthan we have, then Tamil Nadu we have a lot of wind is there. So we have regional energy management systems, and they are operating along with our SCADA station, this SLDCs, right? So they are giving their feed to the SLDCs. Otherwise, it will be very difficult for SLDC to manage these resources. So there will be an interface in between, right? So regional or not regional, renewable energy management centers will be aggregating, controlling the aggregate, and then giving data to the SLDCs, right? So there is a role of an aggregator there, right? It aggregates the variable power, make it look like a firm power, and feed it to the grids, local grids, right? I'm intentionally talking about this. See, when we talk about a microgrid, I'm still worried, what is a microgrid? Can you tell me what is a microgrid? Physically, how it will look like? See, don't in classroom. Physically, if you go outside this room, what will be a microgrid? What will be its entity? Geographical entity. What is that? See, generally we have some examples. Say, Virginia Tech, Professor Saifu was there, IEEE president nowadays. He's in India nowadays for conferences and so. So he was the first person there to have a microgrid in their university, right? So that means they have the resources. Even if they are disconnected from the grid, they can self-sustain. Right. So can you think about all this in our context, where we can have microgrids? And who will the owner? I'm actually striking on this. Who is the owner of that microgrid? Okay, in case of institutes, okay. I come out of the institute, I go to the community. I move out to see, I want to have a microgrid in community, say. Who will be the owner? Yes.
We are going for microgrid, and every households have its own ownership.
But everybody cannot control the grid. So microgrid means you have to operate in islanded mode sometimes. If it is isolated, then all the time you have to operate that in, with the voltage and frequency limits within that given limits.
There will be a independent service.
Yeah.
Independent service supply.
ISO. Oh, yes. So I will call him an aggregator. ISO generally we use for our grid operators. Right. In India, we have ISO. So Grid India nowadays, right? Earlier it was. Yeah. No. Independent system operator is there. Right. So nowadays Grid India. Right. Earlier, I think it was called POSCO, I suppose. Right. What was that called? Now it is Grid India, na? Right. So they are independent system operators, right? So they manage our system, right? So in village, there will be a person, say aggregators, right? Who will be generating, right? And controlling, right? So likewise, what about industrial, commercial and industrial sector? Suppose in this area, in that area, we have commercial and industrial entrepreneurs also, right? So suppose if I talk about a steel mill, they have done DGs, diesel generator sets nowadays, right? Likewise, there may be some captive power stations based upon DG, or maybe see, if you talk about European countries, they talk about CHPs, combined heat and power stations, right? Because they have heating requirements also, right? And see, in case of our fertilizers, we have captive power stations. First we generate, then we use the same steam for production, right? So these are CHPs, captive power stations, right? So my question is how it will act or behave in a microgrid system. Will it be a CHP will be, local captive power station will be called a microgrid? Right. Okay, so we don't have to see theoretically on the paper, one machine, one source of generators and feeding its own load or feeding the local loads, right? Right. So that becomes too theoretical. But once you move out and see practically, you will find the challenges there actually. What are the real and how do they operate? Say, even I did not know before visiting, say wind farm, there will be hundreds of owners in a wind farm. Right. If you talk about renewable in India, how many owners will be there? How many millions of owners will be there? Right. And it's very difficult to control the behavior of the owners. Right. All of a sudden they can say that, okay, we can shut down. Right. Or we can change our outputs. No problem. That is the owner can do for. Right. So we have to see. So I will just show you the classification. I've taken it from Wikipedia, nothing more than that. But I was just trying to think what is a microgrid system. One of my friend is in utility in Haryana, right? So he was 10 years, in 12 when there was a blackout in northern region, right? So he was the controller at that time at SLDC Panipat, right? So he told me, see, there is a thermal power station in Panipat, right? So at the time, maybe generating out 400 megawatts of power. So that is sufficient to feed the local, a vast, in fact, geographical area, right? 400 megawatt was good at the time. Right. So he told me that even if there was a failure from that side, I could hold the grid for half an hour. Right. So he could give orders or direct the people to disconnect the loads in such a fashion that it can hold, right? So in my perspective, point of view, that is a microgrid, right, for a utility. So in India, if you see the smart grid policy, right, you visit ISGF site, right, Indian Smart Grid Forum, you will find that we have a smart grid policy, right? So they have emphasized that we will have around 20 such microgrids, right? So as to take care of such eventualities, like say black start, from where you black start, right? Once there is a grid failure, how will you start it again? There should be some source, right? So microgrid, if it sustains, right, it can provide help to the grid, local grids, to survive again, right? So there will be such issues, right? When we talk about microgrid, actually everybody used a term, this microgrid is there, and I don't know, right? But we have to see from the customer point of view, how we can classify and how we can make it operational so that it can work in a standalone and grid connected, of course, if required, right? So there are not so many examples of operation of microgrids in India and outside also, right? So the concept of microgrid is very broad, but from my point of view, if you are able to control the voltage and frequency and you are able to sustain, so any entity can be a microgrid, right? If you talk about Europe, most of the countries are interconnected. They can share the power generation, the power, right? So I think few years back, there was a solar eclipse in that area in Germany. All of a sudden, there's around 50% of power generated from solar power stations at the time, right? It was a day, right? So it got lost all of a sudden. But they had done the studies before, right? So they could procure the power from, they cannot ramp their thermal so fast. Say 50% of their power requirement, they cannot ramp it fast, right? So they could procure it from the neighbor countries. They could survive. Like, so whenever you have such, intermittent sources, of course, predictable. I'm not talking about their variability. They are variable, of course, but they are intermittent, but they are predictable. You can very well predict with a certain good accuracy nowadays, right? But sometimes there can be a failure, but most of the times you can you have very good predictions about their power generations, right? So when we talk about having these resources, solar and wind, in acting as a major source, right, or similar kind of power station, even if you talk about a gas based and say your biomass, right, all will be connected through inverters, because there we have again variable voltage, variable frequency source. So you have to convert it and make it constant and somehow feed it to the local grids, right? So how to make it behave like a firm power, right? So that is the discussion today, right? So whenever you talk about a grid or a microgrid, it should self-sustain, right? So it should have these two control boxes. One should be the AGC, generation control, right? And then the voltage control, right? So we'll talk about inertia also. What is inertia? What is virtual inertia? Right? When you talk about frequency control, we talk about क्या? हाँ हो रहा है, क्लिक तो हो रहा है. हाँ या अच्छा, okay. And you see that power stations, they provide a lot of ancillary services also, right? Say spinning reserves, right? What is a spinning reserve? How much spinning reserve is required? What is spinning reserve, by the way?
Ready to use but not use.
Ready to use means what? Synchronized or not synchronized? Already working, synchronized to the grid or not? Spinning means they're already synchronized, spinning. As a layman, you can see. It's already synchronized, but you are not using it to the full capacity. Right? Thermal, say. You ask thermal to say ramp down by say 40%. So it has a capacity to ramp up by 40%. Spinning is 40% at that. In India, we have say once we talk about lot of sun and solar and wind, so they'll be ramping down and they'll be having a lot of reserves, spinning reserves, right? So minimum is 55%. Say they're not allowed to operate below 55%. So 45% is the problem, right? So they provide spinning reserves. You must have studied about your unit commitment, then economic load dispatch, right? So based upon all techno-economic criteria, we have first of all economic load dispatch for a plant, then unit commitment for a plant, right? But you see in thermal, you cannot make it to work from cold state to hot, active state or hot state. It will take at least 3-4 hours to start, and then synchronize may take more than that time, right? It's not easy to just start a thermal power station and synchronize it to the grid. It's very difficult job, right? So that is why we talk about ramp rates, right? So ramping, of course, will be when it is spinning, but from cold to hot, it takes a lot of time. So that is why it is called base load, right? And then we have the peaking loads, right? Peaking power stations, peaking loads. So the plants which can ramp fast, right? So they are peaking power stations. If you see the, I'm talking about Indian context, right? If you see the power output from a large hydro power stations, if you see that power output of Terry Dam, say, 1000 megawatt plant. So we'll find that it is working during morning peak and then later in the evening, during evening peak. We don't have sufficient water, or we don't have surplus water so as to run it as a base load there, right? Of course, there is a pumped hydro power station attached to it also, right? So whenever there is a surplus, it can pump the water back to the main reservoir, right? And can be used for picking purpose, right? So, and we have, we have a lot of potential available for pumped hydropower stations in India. I think till date we have around 5 gigawatts or 6 gigawatts of pumped hydropower stations, right? But a few days back only, I was told that we don't nowadays we don't require large reservoirs for pumped hydropower stations. Even if you have a run-of-river power station with a small catchment area, I mean small reservoir, right? So he was talking about only 1 TMC of water, right? So you can have a pumped hydropower stations of around 400 megawatts of size. So it is a new thing. Say even if in run-of-river power stations, if we can have a small storage and use it for pumped hydro application, because that will provide you peaking powers, which is otherwise very costly to have from conventional, say, diesel generators or other types of sources, right? So I'll talk about energy storage later on. How do we provide the frequency control, inertia into the system, right? So this non-spinning reserves for frequency regulation, contingency reserves are there. Say in India nowadays, we have one nation, one grid, right? All the 5 regions are interconnected, right? Till of course we don't have sufficient tie lines to interconnect our regions, but we shortly will be having, right? So we will be able to exchange much power among the regions, because you see in India we have an advantage. Say we have winter here, right? And in south we have a bit of a summer-like season, right? So here sometimes will be rainy, will be using hydropower stations, right? So we can transport the power, that is seasonal variations. We can take care of the seasonal variations and export power to other areas, right? So generally our ministry or government talks about not one nation, right? We talk about one world nowadays. We have ties with the neighboring countries, or we can export power from import power from neighboring countries, right? So especially in solar, nowadays we see that we will be having solar power from 24 hours, right? Say how it is possible. It is possible if you can export the power or take advantage of the time shift, right, which can be provided by having a grid connecting all the nations, right? See, even if in India we have one time, right? One time zone, I suppose, in India, right? But you see northeast and our side. So there will be a difference of, in sunset, there will be difference of 1 hour, right? So 1 hour is also very good for us, because during that you have peaking. Say once the sun sets, you don't have solar, but you have a peaking load, right? If you can shift it by 1 hour, right? So you'll be saving a lot on that peakings, right? So then it provides you the voltage support and black start also, right? I'm listing this why our solar and thermal should provide all this, right? They should be able to provide all this. Then and only then they can replace the conventional one, right? Just read this. Control and protection are difficult, as all ancillary services for system stabilization must be generated within the microgrid. We have to generate within that microgrid, right? Ancillary services. And low circuit level, short circuit level can be challenging for protection system, right? I tell you, very difficult proportion in our distribution system. I generally heard about the mishaps in our distribution system. Suppose there is a fault in a local feeder, right? It breaks down somehow, it falls on the ground, right? And there is no tripping on the relay, on the substation. Why? The relay does not trip because the short circuit level. The impedance of the line or the feeder is high, voltage is low, so the current will not be much so as to operate the relay. And the person who comes into contact, say any person who comes into the contact with that line will get a shock. Right. So generally I hear about all this. Right. So that is a problem. That will be a problem when we talk about protection of a microgrid. Right. And there are other issues, bidirectional power flow, because there will be bidirectional power flow in microgrids, right? There will be so many sources connected, not a single source. It will not be a simple radial feeder, right? So there will be bidirectional power flow, and conventional protection system is not going to work. Yeah, you have to you have to find out other means so as to sense the fault, right, and then operate, right? So conventional are not going to work. Okay. And this is for heating and cooling besides electricity. So generally it's for European countries or cold countries, right? So they have a lot of heating requirements. Nowadays, they are facing this heating requirements are there. So why they are talking about heating and cooling requirements here? Can you tell me? I was talking about CHP, right? Combined heat and power stations. So you can see when you have surplus, you can use it for heating purpose or cooling purpose, right? Later on, and otherwise you can store them, right? You can store it for peaking hours, right? In India, we are working on this. Say demand. We call it demand side management, DSMs. Right, we want to shift the load from peaking to off peaking, right? So as to make this curve flat, load curve flat, right? So see, I give you an example. How do we store? Thermally store. So there is a mall, big mall in Bombay, say, right? So they have their cooling requirements, say AC, air conditioners are there, cooling requirements is there. So what they do is during off hours, when TOD is less, they have TODs, time of day price is there, tariff is there. When TOD is lesser, they convert water into ice. They store it, right? A small system. We're talking about a small system for that mall, right? So they have a chilling plant, right? So they convert water and store it. But during day when TOD is high, they use that for cooling their building, right? So this is a small project. So that is like a DSM they are doing. So in India also, say when we talk about agriculture loads, I'm talking about a community, a microgrid in agriculture loads, in a village, rural areas, right? So when we have surplus solar, right, if we integrate more than say 15% or 20%, there will be over generation during the day, right? You don't have sufficient load, net load will be lesser, so there will be an over generation, right? Net load will be lesser means thermal has to run to minimum, right? Then you superimpose wind, superimpose solar, right? So you will have over generation. Europe is facing this. They are having over generation during day. What is the problem in over generation? Can you tell me what is the problem if you have over generation? You have invested a lot of money on this power. What is its marginal cost? We call it marginal cost. What is marginal cost? You are not getting any penny out of it, right? So you have invested a lot on that, and you are not getting any out of this, right? So how to utilize how to utilize that surplus power? You have to shift your load. So we talk about flexible loads. Flexible loads which can be shifted from peak to off peak. You have a washing machine, right? Okay, you dump your clothes, put a timer, set a time from off peak to peak, from peaking to off peak, right? Your bill will be less, right? But when we talk about a large size, say agriculture, say India, we generally in our area, we see that they are being served during night only, for say 8 hours. Because we had that in mind that say we have surplus during night. But if you see it today, if you see the Indian load curve, right, you don't have surplus during the night also. Because our AC loads, HVAC loads, heating, ventilation, air conditioning loads has now increased. So if you see the daily curve of daily load, you will find that you don't have any minima. You will not find any minima there, right? But of course, there will be a gap between summer season peak and a winter season peak. Of course, it will be there, but curve will look like to be same, right? So agriculture load has to be now, if you have surplus, it will got shifted to day, right? So that you can use that surplus. Agriculture load, we have very good agriculture loads, right? It will be shifted during the day. So we'll be using all this DSM, then energy conservation and all, right? Okay, I have deviated too much, I suppose. Okay, come back. This is about wind, right? It's a good for solar also. Same thing is happening for solar, right? Reactive power capability. Generally, we need reactive power capability whenever there is a fault on the system. For fault ride through, we need reactive power capability. So we inject reactive power so that we can maintain the voltage level, right? So that our relays or protection system can operate. Otherwise, our protection system is not going to operate. If the voltage falls too low, then even our relays are not going to work in that time. Then this is a bit on reactive power. Reactive can impact of active power fluctuations. It will change the voltage, right? At the connection point of common coupling, we say PCC, right? So if we are able to control the reactive power injection, right, we can vary the voltage little bit. So I'm talking about all ancillary services, right? I think I will come to this later on. Controlled inertia response. Okay, I can discuss, no problem. So in thermal power station, you must have heard about the frequency response, right? Okay, how much fast it is? How do we provide, first of all, the frequency response? See, first of all, we have inertia taking over the mismatch, right? So this is because of the inertia in the machines, right? So you have inertia control, right? But it will not sustain for long. Long means it will sustain only for few milliseconds, right? And then you have to provide the backup. So then you starts your primary backup, secondary backup, tertiary backup, right? It starts, right? So, and what about this frequency response? How much fast it is? How much time it will take? Suppose there is a deviation in the frequency. How much time it will take to come to the normal one? You're talking about seconds, right? So, but here I have written that you are inverter based. These are all inverter based systems, solar and wind, right? Can provide you fast frequency response. If it is capable of providing, it can provide you the fast frequency response, right? So how it can be provided? So if you see this power curve, wind power curve, generally you operate for a particular speed, for a particular wind speed, you operate the plant or machine at MPPT, right? This is where we operate so as to get maximum power out of it. But if you have surplus, I'm talking about surplus now, right? If you have surplus, like in Europe nowadays, they don't operate their plants at MPPT. They operate the plant with a power which is lesser than the MPPT, maybe around 70% of the MPPT maximum power which is available. So that means now they have a surplus of power of delta P now. 30%, say 30%, 20%. They have surplus. That means they are curtailing the power at that moment, right? So that whenever you need it as a store, right? So as to provide you the inertia. This is called virtual inertia, right? It's not a physical inertia into the machine, right? But it is called virtual because you are operating the plant at this point, but the plant has capability to operate at this MPPT at the time. So you have this much as surplus and you can pump it very fast because this is an inverter based system. So within milliseconds, few milliseconds, you can pump it. So that is another F is there, fast frequency response, right? This is how we can provide the inertia into our renewables. That is, you have to curtail. Curtail does not mean you have to waste. You can store it also, right? So you have to curtail, and whenever there is a requirement from storage, you shift it to from storage operation. You shift it to the grid. Instead of storing, shift it to the grid, right? So this is going to happen because I'm talking about over generation. There is no marginal cost, right? So that time you can store it or waste it. And that is why in Europe you talk about heating systems. They use it for heating systems, right? For heating purpose they store or use directly for heating purposes, right? So the inertia which is not inherent into the wind back-to-back system power stations, we can introduce this, right, by curtailing some of the power which is available at that time, right? So that is how you can control the frequency, right? Okay, one more question was there in my mind. What about the frequency? What is the frequency of operation? How do we set the frequency of operation? So in India, we say it's 50 hertz, right? Right. So how do we set it to 50? Our machines say it's very simple for synchronous machine. Say we have 2-pole machine. It will be run at 30,000 RPM, right? So you'll get 50 hertz. I think it is same. It is so. So there is a frequency, physical waveform is there. I will call it a template, right? Right, unit vector, you will say in electrical terms. If you talk about, it's a unit vector, say it's a template. You're getting a template. You can multiply it by any number, amplitude, right, and get any value for your voltage waveform, right, or current waveform even later on for the loads, right? That is 50 hertz. If you have a lot of synchronous machine, see in India we have a lot of synchronous machines operating, right? So every machine has to be synchronized to this 50 hertz system. So whenever there is a mismatch, there will be frequency deviations, right? Machine will slow down or will accelerate, right? So, but your machine, incoming machine, that has to be synchronized. You know how this has to be synchronized. Okay. What about inverter operations? How do you set frequency there? Reference from the grid itself. PLL, right? You take it from the template, you take it from the grid itself. 50 hertz. Can you set it 40 hertz? Okay. Yeah. T-connected. Okay. Independent operation. If you have independent operation, you can change the frequency, right? So from that, that means you have to only set only. You have to feed this figure 40 hertz, 45 hertz, 50 hertz. You don't have any machine, inertia, right? Like thing. You have to simply simulate a curve which looks like a drooping characteristics of a machine. How do you coordinate between a synchronous machine and a solar PV powers? Right? Suppose you have only 2 synchronous machines, you must have studied. You have their drooping characteristics, right? Intersecting, and that will be point of operation for frequency, stabilized frequency, and the power sharing. But what about inverters? Do they have drooping characteristics? Yeah. Do they have drooping characteristics? Yes. Where is the slope? M, where is M? M1, M2. Where are M1, M2? You just feed M1 is this much, M2 is this much. That's all. And why you're doing this? I don't know why you're doing this. You are following the same modeling, mathematical modeling, and doing simulations. Because we are imitating the same control algorithm, right? So inverters, say one inverter will droop by say 0.1% from full load to from no load to full load. Likewise, another will do it, right? With maybe with different, that depends upon the capability of that inverter source on that side, back side, right? Whenever they intersect, so that will be set. Why not through communication then? Why you cannot set it through communication? Power sharing, which you are calculating, make it work at 50 hertz and communicate. You can generate this much, and you have to generate this much. Even if you are able to generate, say, 100 megawatts, but there should be a signal. We need only 50 megawatts from generate at 50 hertz. What's the problem? That means we need a communication system which can act fast, right? Through communication also. Nowadays we can do it through communication also. Earlier we were relying on the machine, say, characteristics, right? Droop characteristics, right? But our communication nowadays is very, very fast, right? So we can now communicate also. We can calculate and communicate. Okay, this is your power sharing, right? So that is why this question was there in my mind. How do we set frequency? 50 hertz. What is 50 hertz? In conventional machine, it was because of the moment of the machine you're getting. But nowadays you can feed any parameter, right? So you can exactly work at 50 hertz or not. That is a question. Can you work exactly at 50 hertz? Okay, you can just think later on, right? Can all the inverters set the frequency 50 hertz, exact 50 hertz, no drooping? Okay, okay, you could generate this much, that much. Okay. This is the time scale I was talking about. We have inertia response initially, right? IR, inertia response. So, see, initially it will try to improve, right? Then we have primary frequency response, primary source, and then secondary. So then AGC will take care and it will try to change the or increase the input, right? So say in some time your system may come to the normal conditions, right? So actually I was in the technology advisory group of Enercon India Limited. They had some patent issues regarding operation of wind power stations. So I'd been a member of the team to take care of the patent issues of that. So then I studied the grid codes, right? What are the grid codes for integrating wind or nowadays solar also into the local grids, right? So the in this document we have connection codes, how to connect it, and then operation codes. During operation, right? What we have to see: voltage variation, frequency variations, and feeding power. How to feed power into the local grids, right? So I stop for a few minutes here. If you have any question on this, what I'm talking about. I will talk about voltage control later on, right? How do we control the voltage, right? So, any question? No. Nowadays it's very tight. Within 0.5%. I mean, within 0.5, 49.5 to 50.5 maximum. No, not 10%. 1%. And if you see our frequency nowadays, it will not very much. It will be 49.99, something like that. They are very ISO. I was talking about ISO, right? Or independent system operator looks after all this, right? And see, when our grid failed, right, northern region failed, there was an overdrawal from the states. They were overdrawing, right? And because of that, one line failed, right, tripped, and that led to the tripping of all cascading, right, cascading of the power lines, right, tripping of power lines, and finally there was a blackout for this reason, right? So overdrawing nowadays they don't allow much. They are very particular, right? So that is why you see the frequency band nowadays is very small. Yeah, earlier we had tolerated 48.5 also, no problem, right? But nowadays 49.9 above, right? Because see, we are using better communications SCADA systems also, right? SCADA and all. So we have better control nowadays. Now the person at NLDC can oversee. Earlier, see, the supervisory control was there, right? So, I mean, at lower level, the person at the top could not see what is happening downstream, right? But nowadays, at every level, SLDC, then RLDC, then NLDC, you can see all the data, generation data, load data, and see. So they don't allow much deviations, right? So have you studied about grid code somewhere? Not till date? Okay, then I think it will be new for you. So in actual practice, whenever a power plant right, operates, say generator operates, it has to take care of grid codes. How do you connect? And then how do you operate the generators, right? So simple topology, I think, is a simple topology. You have generator, then DC link, then inverter, then you have a local transformer, because inverter's output will be around 400 volt, right? So you step it down there only to say 33 kV generally nowadays, because minimum level is 33 kV nowadays when you connect our DRES. So there itself will be a 33 kV transformer, right? And will be connected to a main transformer. There will be a feeder, right? And so many such feeders originating from the machines coming to a local collection station, right? Substation. That is LV substation operating at 33 kV, right? That substation then will be connected to the local grids, right? And distance may vary, depends how far it is from the local load centers. It varies. Say if you talk about Jaisalmer, the nearest substation, local substation, they will find at Jodhpur, 300 kilometers away from that, right? So you will have typical problems related to that feeding power at the long distance, right? Okay. You see this term voltage withstand voltage variation. Voltage withstand limits for wind farms. Means wind farm should be able to operate. Say, suppose it is connected at 33 kV level. So voltage limits are plus 5% to minus 10%. They should be able to operate in this range. If it is beyond that, you have to disconnect. You have to disconnect, right? So suppose the voltage has exceeded more than 5%, disconnect. Right? Even if you are able to generate, you cannot. You have to disconnect because voltage is high, right? So it can damage the switch gear, which is there nearby, right? Maybe at the substation, right? So it can damage. Especially, I was today only I was studying a report. Say our especially voltage transformers, they're prone to this, right? So when the voltage exceeds, it will blast, right? So that's a very typical problem in case of solar and wind. So at PCC, there is a voltage rise. There is not a voltage drop. There is a voltage rise. I will talk about this. This is a serious problem. And if voltage rises beyond a certain limit, say 10%, the switch gear is not going to sustain, right? And shutdown means shutdown. You will be losing a lot of money, right? Why? Why? Yeah. Yes. Actually, I have not gone in detail, but it may be because of the impedance of the lines. Because in case of 400 kV, you have large conductors. Impedance is lower. For them, you have set lower values for the voltage variations, right? I think so, but I have not gone in details why they have set differently for different types of. But in case of distribution systems, generally it is 10%, right? Because you have large impedance. I mean, resistance is larger, right? So you can go for. I mean, you can tolerate more voltage. You can have, in fact, more voltage variations. So, okay. Now I'll talk about the main issue, voltage. How do we control the voltage? Right. First of all, I'll talk about conventional radial system. Say there is a high voltage substation here, right? And to this high voltage substation means it will be feeding around hundreds of megawatts, right? A big entity. It will be feeding a local 33 kV or say 66 kV distribution system or 132 kV low voltage substation, right? And load connected to this will be lesser, maybe at the most 10 megawatts, right? For 33 kV, it may be around, it can go beyond 10 megawatts. So I'm just giving the scale of power you can feed in, right? So this now to this LV will be connected your through the feeders will be connected the local loads, right? So I suppose there is initially there is no wind say generators here or say any DG here. So how do you maintain the load voltage within the prescribed limits for the customer satisfaction? How do you supply rated voltage at this customer level to this load? What should be the voltage level at LV grid? Sending end, I will call it sending end, say, right? And this is receiving end, right? So normally, what should be the voltage? In normal case, only loads are there. Flow is in one direction only, radial system. What should be the voltage here? So as to maintain unity, per unit voltage here at the receiving end. The drop. And feeders are generally resistive in nature, right? So that will be in phase with the voltage. Drop will be in phase with the voltage, not at an angle, perfect angle, right? Okay. That means its impact will be more. You are directly subtracting or adding or subtracting there, right? In phase. So that means this voltage has to be higher. Say 1.1 per unit, right? Okay. Now, in second case, I assume that you have a generator now here, any generator, which is feeding, and it is feeding in such a fashion that power is same as that of your local loads. Net power or net current flowing through the line is 0, right? So that means what will be the voltage here? Voltage at receiving end. See, there is a transformer there at LV substation. It has a tap settings. You must have heard about OLTCs, on load tap changers. So the tap is being set for 1.1 per unit, right? And that fellow does not know what is happening here. No idea, right? Because this will vary. This is going to vary, right? So that fellow is not going to listen, right? Okay. So what will the voltage level then? 1.1 here. Okay, it has come to the limit. It has come to the limit now. Now, if this power generated or fed is more than the load, then the direction of this current is going to reverse. This fellow does not know what is happening, right? This sending in. What should be the voltage here so that it can feed reverse? It will exceed 1.1, depending upon how much you are feeding, reverse feeding. Right? So that means there will be a voltage rise here. Dangerously high, depend on how much it is feeding to the back. So when it exceeds, your switch gear is going to fail. One is this. Another, I just talked about I've shown you the tolerance limits. It has exceeded the voltage limit. So voltage relay will trip. Will make the plant trip. So even if you are able to generate, you cannot feed. Plant is isolated, tripped. Right. So that means, because you see, this machine does not have any AGC. I was talking about thermal. There they have AGC to maintain this voltage level at PCC. Right. But this poor fellow does not have anything. Right. I will make him rich, don't worry. So how to take care of this voltage rise? How to reduce this voltage rise? Can you suggest me some means how to reduce this voltage rise? You see, more we feed, active power we feed, more will be the voltage rise. Right? So how to control this voltage? Changing the reactance, you see, is a small feeder. It will be having lesser X by R ratio, right? More resistance, right? It's a resistive, will be purely on, more on resistance. How can you reduce the resistance of line? Can you reduce? Inductor will lagayenge, don't worry. Can you reduce the resistance of line? Okay. One of the interviewer asked me this question in one of my UPSC interview, right? So I was just actually having one project on reactive power control, voltage control, for a distribution system, reactive power control. How will you reduce the voltage for this distribution system and reduce the losses, right? So again, I gave Fadu answers, right? So then he simply told, you can have another line in parallel. That is called augmentation. You add another line so that in parallel, so that overall resistance decreases and it becomes half, say, suppose same conductor, half, it becomes half. That means now the voltage drop will be half. Right? And you can feed more also. Right? So generally, you see, whenever we have such power station DR in local grids, right? Our lines are same old one. Right? Otherwise, also we have to augment our capacity, line ampacity, right? Capacity of the line, right? So that we can feed it to the grid, right? So that is very simple solution, right? Okay. So that is why I had written at the top simply adding another line, right? Then reactive power injection. This can be done at where will you provide reactive power injection in our distribution system? Near to the loads, as near to the loads as feasible, right? So it is through, say, depends, right? If you have simple loads only, you provide capacitive compensation, right? But in this case, you have to provide inductive compensation, right? And it should be connected. You see, I have not shown, in fact, here. There is a transformer here also, right? As I have shown, you can just think about this. There is a transformer. I record back. You see, this transformer is there. This transformer is there, and finally, this transformer is there. I'm talking about PCC, right? This is at PCC, right? This transformer is there. Right? So there is a transformer here. So on which side of this transformer you will provide reactive power compensation? Suppose you want to provide reactive power compensation, inductive, right? The question is, first of all, is very pertinent in our local grids. Can reactive power compensation control the voltage? See the diagram again. Your feeder is more or resistive. Reactive power compensation will come into effect where you have more X by R ratio. right? So in that study, I will give the study. For a 2 megawatt of plant, you need 4 MVR rating of the reactors. MVR lagging, right? So as to maintain this voltage constant. What will happen if you are injecting 4 MVR from this side? 2 megawatt was active, 4 MVR you have to inject. Okay. It's an actual study. I will give the study, right? Done by my friend, right? So yesterday I had permission so as to show this, to show the study. They have done it with PRDC, right? So what will happen? What will be the consequences of injecting 4, double of the capacity? What will happen? What about the current you are feeding? What is the effect of that? Current will be almost double. Losses, what about the losses? He says losses will increase to, if it is running at full load. Full, I'm talking about full, right? 44% losses will be there in the feeder. Can you just think of this? Losses will be tremendous losses. When you are feeding 5%, right? Percentage losses will be much more. So I had also this concept in mind. Okay, inject reactive power and have a voltage control, right? But practically or theoretically, even if you see, because of the lesser X by R ratios, right? So that is not going to help you much, right? So this was through the additional component, right? But there will be again a coordination problem, right? Between the what we call it coordination among the reactive power compensators. See, whenever there is a change in the voltage, transformer tapping will change. With the change in voltage level, reactive power controlled by the transformer or fed by the transformer will also change. So one will try to increase the reactive power compensation, another will try to decrease. So there will be ping pong. One will be increasing, another will be decreasing, and there will be ping pong, right? And in fact, that will be actuating the tappings, OLTC tappings. And have you seen the OLTC tappings? How OLTC works? Say you have additional winding, right? Number of turns on a transformer, additional, right? Then you tap it. So generally you have a tapping of say 0.5% plus minus 5% steps, say up to say 2.5% or maybe 5%, right? Right, you can change. But what is the nature? It's inductive. It's an inductive circuit. Right. So when you change the tapping from one position to another position, you change the direction of the current flow within that. So there will be circulating currents, right? And may damage the winding. Right. So the power station operator, they are just afraid of this. They don't allow much tap changings. Step changes should be minimum, right? So that is a difficulty in operation in case of variable loads, variable generations. Power fed will change, voltage level will change, right? So there will be change in tappings, right? So switching, there will be number of switchings. So it has been there is a study that in a day within a day you will find there are 40 switchings. 40 switching is very dangerous, right? So whenever you have switching, there will be heat generated inside, and maybe sometimes very fast, right? So it may lead to fire also, burning and fire out, right? So it's not easy Theoretically, we'll say that by type changing we can do it, but practically it's very difficult, right? So we have to minimize the switching in OLTCs. That is the main aim, in fact, while you control the voltage, right? So that was another technique. Say we inject reactive power, but as I told you, it's not advisable to have reactive power injection to control the voltage at low voltage levels, right? And see, there is a transformer. Yeah, I got it. There are two sides of the transformers, right? One is low voltage, another is high voltage, right? Where should you connect the reactive power compensator, on the low voltage side or a high voltage side? On the grid side or on the grid side or a generator side? If you connect it to the low voltage side, when the generator side, right, current will be flowing through the transformer, right? So that means you are injecting too much current into the transformer. That means it cannot feed the active power there. Conductor capacity is same. If you are injecting too much reactive, you cannot feed active, right? So generally we use it on HV side, means on the source side, right? Even if you put it on the source side, losses will be tremendous. Line losses will be high, right? So it will in fact negate the advantages, right? So it's not advisable. Okay, then okay. Now I come to some research work, right? What the people have done. All masters of R&D, right? Research only, not development. Only research, no development. And this is what we have already seen. Actually, this is just to show you there's a conflict, right? There's a reactive power compensator, right? So it will be conflicting with the OLTC. So generally what we do is, in the distribution system, we change their say dead bands, right? There will be a dead band, right? There will be operating say time settings. Initially, see, out of these, which should operate first? Suppose we have say a reactor or say capacitor here for compensation. Which will act fast? Tap changer or a capacitor here or a reactor here? Capacitor. So initially capacitor will take care of the variations, reactive power compensation, right? But you see, its scope will be very limited. Otherwise, you need a huge capacitor bank for that, right? So then, with a time setting or time band, this OLTC will work for larger voltage variations, larger than the capacitor limit, right? Right. So there is a hierarchy set, right? So OLTC will change its setting, then the minor variation will be taken care by the reactive power compensators, reactor, say capacitor or reactor, whatever it is, right? So that is called coordination among the reactive power compensators in a local distribution system. Now, when you are adding a DG, right? DG is what? Statcom, again, right? It can operate as a compensator, reactive power compensator. It can also inject reactive power along with the active power if needed, right? So another reactive power compensator comes into action. So now there are three. OLTC is there, then your reactive power compensator is there, then DG is there. All will be toggling, right? So as to control the voltage, right? So you have to coordinate by time settings, right? And their limits. If the voltage variation is in this limit, this should operate. If it is within this limit, with the time, with the dead band of this, it should operate. Right? So it's not easy. This ping pong is going to burn your OLTC. There will be a lot of switchings, right? And finally burn. Right? So that is coordination. So this is what we have in grid codes, right? Say how to keep this voltage within the prescribed limits. So see, I think we concentrate on this side. It's a rated voltage here, right? So if you have the voltage up to this, say it is not the tolerance limit, say maybe say half of the tolerance limit, right? Then you feed full power. Whatever is being generated, you can feed full power. But once this limit is crossed, right, up to the tolerance limit, you have to decrease, you have to curtail the power generation, right? That is the operation. How do you operate your power stations? So there will be curve fitting. If the voltage is this, generate this much. At that particular speed, what I'm talking about, right? If voltage is this, you have to generate this much. Looks to be very simple, but it's not very easy to do it practically. Okay, this is Yukansky. Again, power factor angle. So again, how much power can be fed at different power factors? So I tell you, generally when we have inverter based power generators, we can set the active power output and reactive power output, right? ID, IQ must have, right? Components. So generally the generator will like to feed only active power. It will put IQ is equal to 0 because he has not been paid for that, for injecting the reactive power. He has not been paid for that. But if he injects that, inverter output capability will be lesser. You will not be able to feed the active power, but same active power, right? So generally I have seen they put IQ is equal to 0. Whatever active power is available from the source being fed to that. So that means we have unity power factor operation for most of the plants, right? And generally they are being told to operate within 0.95 power factors, leading lagging power factors. So that is why if it exceeds that limits, then disconnect. Yeah, this is with frequency. So up to a frequency which is slightly above the rated frequencies, you can feed the maximum. So beyond that, if the frequency of the system is more, it is assumed that you have surplus now, right? And your machine may be at a danger, say, especially thermal power stations, right? Your generators will be at a danger. So you have to reduce the output. So the wind power stations, they will be asked to curtail the output by pitch control, say, by changing the pitching. So they have to reduce. And finally, when the frequency is too high, you disconnect. You are not needed. Disconnect. Right? So there are opportunities. When they say that you disconnect, can you still run and store it somewhere? When this grid code started, I think maybe 13 years, 14 years back, said draft, right? So we generally thought, okay, we'll disconnect because there was a subsidy, there was lesser money involved in that, right? So we thought, okay, it's free of, it's coming free of cost. You don't have any fuel cost, right? You can disconnect, no problem, right? But nowadays, you see, you can store it somewhere, right, and use it. Because connection and then disconnection and then connection is also difficult. It will take time. right? You have to synchronize again. It will take time. Losing on that. Okay, so yeah, this is how our inverter-based system has to support nowadays. They have to provide the reactive power capability, right? So whenever there is a fault, they are not allowed to inject active power. They will be asked to inject reactive power, 100% rating for reactive power, right? And that will support the voltage at the time of fault. And that is why you see, oh, sorry. So you see, it should not, when there is a fault, this voltage will reduce maybe 50%, 60% or 70% of the rated values. So till the fault is cleared, your machine should not trip. It should provide only the reactive power. That's all, right? Where the active power will go? Suppose there is a windmill. You are not feeding active power. What will happen to the machine? Where it will impact? This active power is going to be stored. Where? Same, when machine is there, you are not feeding active. Where will the active power go? What will happen? It will? Yes? How? This time is very short, you see. Fault clearing time kitna hai? What is the fault clearing time? 3 cycles at the most, 60 milliseconds, right? Try to understand this. 60 milliseconds only. What will be the voltage at the DC level, DC link? Will it rise? Huh? Yes? Yes? I could not get. So you're not feeding active, DC voltage will rise. Capacitor जो लगा हुआ उसमें DC link पे, its voltage will rise, and there is a trip setting there also. If it is beyond 10%, it trip. Can you store it somewhere? There is a inertia, there is a synchronous machine there. You maintain the DC constant and accelerate that machine. MPPT. W उसका change कर दो, बढ़ा दो थोड़ा. Accelerate that machine. हल्का सा. So it will store. And then if it is connected again to the grid, push it back. Come to the normal speeds. MPPT पे आ जाओ. Right? So this you can do in LVRT. Okay, so I think you can understand this now. Up to this, it should not trip, because after that was fault clearing time, fault will be cleared, right? Or disconnected. So then voltage will improve, right? So it should not trip. Yeah. Now research. Okay. How to maintain this voltage constant at PCC? What is this? You see at PCC. This is PCC, right? Solar is there, right? Solar is there. Then there's a DC link. Of course, inverter converter is there. Then what is this? Series injection, DVR. All electronics people, they can understand us. This is what? series compensation, DVR, we call it DVR, right? And this is what? Shunt injection, right? So this is StatCom. So you can maintain the voltage by injecting in series, right? Like we do in phase shifters. Phase shifting transformers, I think you must have heard about. Phase shifting transformers, we inject, right? We tap it and then inject. Tap it shunt and then inject it in series, right? So we can control the voltage. So same, power electronics has done that. So this becomes unified power quality controller. Unified means shunt as well as series compensation, right? But you see the cost involved in that. I don't know how much cost involved, right? Because you are using again a power electronics device. This additional you have, right? So I don't know when it will come into practice, right? To control the voltage at PCC, right? Have we used somewhere? Yes. Oh, my strength. So you are also participant?
Yes, sir.
So okay, you missed my lecture. So in fact, she must have
Sir, I am attending online.
online. So this is same as that I have delivered in the class? Almost, okay. So she was my PG student, right? Okay. So this can be done, right? You can control the voltage. Now I've taken something from this person who has done a very good work now. In fact, it can be implemented, right? So what he says is, see, whenever we are feeding active power, there will be voltage rise, right? If the fellow who is there at the HV substation, medium MV or HV substation where we are feeding, if that fellow has an idea about how much power is being fed from the source, it can change the tappings. It can change the set point, voltage set point. See, it's very simple. When the direction of the current was towards the load only, generally we set the voltage at higher values. Set points are higher, right? But when it sees, how it will see? How much current it is getting back, right? If it sees that you are getting currents back, right? Power back, change the voltage setting there, right? You decrease the voltage setting. When we are being fed from the generator side, instead of having voltage setting at 110, which was earlier there in case of simple loads, right? Make it 0.9, right? So that it is 1 per unit at the generator side, right? Very simple solution that you generally do in case of your what you call power factor improvement. In case of industrial power factor improvement application, you have relays which are based upon the load settings, right? If the load is more, connect more capacitor bank. If load is lesser, connect less capacitor banks. So likewise here, if you are being fed more, decrease the voltage setting there at the substation, right? But it has to be a dedicated transformer. Otherwise, you see the loads which are connected to the same feeder or the grids, they will suffer, right? That means you need a dedicated transformer, right? A dedicated transformer which is taking care of the power variations at that particular feeder level, right? So you need a dedicated. So the case study which was done was a retrofitting, in fact, for a particular old power station. So the local utility said, we cannot have a separate transformer for you, right? So then what they did, they used a they used another isolating transformer here in between, right? So that depending upon the power being fed, they can change the voltage level at the at the entry of the their generator here only. That's all. When they retrofitted, they had additional transformer, right? And see, when the voltage was higher here, when they were feeding more, they reduced their LV side voltage, right? So it is like having a DVR here. I had shown you the DVR there. It is like having a DVR here, right? They have put a isolating transformer, right? Of the same, actually, it has to be of the same rating also. Another cost involved in that, right? So that was another solution given. But I think this solution looks to be very attractive. You see now. See, when the power is flowing in one direction on the load side, voltage setting is higher, right? But when it is flowing reverse to the substation, voltage setting has to be lower. So this can be done. But if there is a dedicated transformer meant for feeding this type of loads, right? So this was the solution. I think you can work for that. So I have given you the reference also, and I think we should recognize. So very simple, you see, very simple topology, control technique, no hi-fi, simple, change the set points only with some certain dead bands, that's all, right? So they call it droop control method. Droop means depending upon the power, right? If power is this much, reduce the voltage by this much amount, right?
This point will set according to what parameters?
No parameter, simply see the power being injected into the substation. Relay लगा उसमें monitor आ रहा है आपका. So simply depending upon the current, you have a logic, right? Change the tap setting to this position. Simple. Earlier it is based upon voltage level. Now you make it current based. If current is this much, tap position is this, right? If current is this much, direction is this, tap position is this. Yes, but that is of course that is why you see the bands also, dead bands also in between. In fact, we don't want fast operations, right? Operation is okay, but we don't want more switching also, right? So 2 or 3 step. See, they have shown that within 2 or 3 voltage settings, they are able to maintain the voltage within the given limits. Only with 3 settings, right? So there will not be fast switching. So I think I don't talk about microgrid, right? So you must have been taught a lot about microgrids, right? But I give you only 2 questions, right? Think about a microgrid, practical microgrid, right? How it will look like, and who will be the owner of that? Who will control it, right? Don't make it only a research problem, right? So who is the owner and how it will be operated? That is a basic challenge. Who will operate it, right? Because small microgrids, and how the regulator is going to regulate them. Regulator के लिए भी समस्या हो जाएगी. Central means what? That is why I told you, these renewable energy management centers, they have come up, especially for renewables. I don't know for microgrid what they are going to do, right? So I had not touched upon the energy, storage systems, right? So Have they been taught about energy storage systems? Because you see, I've told about the inertia, right? So this inertia I've taken from curtailing the source. But if you don't want to curtail, you should have some storage, right? So you have to see which is the feasible method of storage energy. We talk about batteries, right? So we will talk about hydrogen later on, right? So any question?
Husband can ask for question. There is no time for interaction. We should have inquiry. Yes. You can put up the question.
No questions? Huh?
About Prof, not of ABC, and not about renewable.
In case of
Yes, solar plant.
generation control. Yeah, in generation control, you have to go for this FFR, fast frequency response, either curtailing or by storage. That is how you can provide inertia. That becomes your AGC. Right? Yes. Below MPPT. MPPT is maximum. You curtail it and use it or throw it. And think about the cost involved. In fact, generally we don't think. किसमें किसमें do control for voltage control. Droop तो इसलिए उसने नाम दे दिया है. Droop means it look like drooping characteristics. इसलिए ड्रूप बोला है और कुछ नहीं. कॉस्ट का इन्वॉल्व नहीं है इसमें. How cost is involved? I don't.
You said that for a converter, we take any M or N values, drooping value 0.01. What is the physical significance? Why we are taking any of like for a converter we are taking 0.1%. For
Yes.
other converter we are taking 0.2%.
Actually, one of my students, he modified instead of a straight line, he made it a curve, right? So what we did is for M, the slope initially it is higher, right? Then when the source is depleted, right, it can be lesser. So it's not that only straight line is going to fit. You have to fit a straight line. So we have made it looks like a curve. And well appreciated by Professor कौन थे, ISC बेंगलोर से थे, कौन थे, कहते हैं आपने तो नया ही काम कर दिया. हमारा IEEE में काफी पेपर है, ऊपर देख लेना उन पे, मोस्टली इस पे जो हमने डिस्कस किया तो कॉन्फ्रेंसेस के हैं हमारे काफी.
There is microgrid, called AC microgrid, and in which aspect it is different compared to conventional grid.
AC microgrid. That is, I am confused in fact. What is AC microgrid? Right, we have AC. I mean, your load is being served AC, right? And it's connected to AC system grid. That's all. So how it can be different? I don't know.
Because many people work in the root control. In AC microgrid. Similarly, if you see two power plants generation, they are also work. They also work based on the.
You make it per unit, then you can use a droop. You make it a per unit system, right? Even if in AC DC also, you make it per unit, na, for voltage, right? So then you can have same drooping characteristics, same, I mean, modeling. How do you coordinate among AC DC microgrids? By droop only, right? So not in power, that will be in voltage. Droops will be in the voltage characteristics. बट आजकल कम्युनिकेशन का भी काफी रोल हो गया. इंस्टेड ऑफ ग्रुप ना, यू कैन गो फॉर this communication technology. You can use communication technology, right, for sharing, power sharing. हाइब्रिड भी बोल देते हैं, फिर किसने आगे हाइब्रिड भी शुरू कर दिया है, दोनों लगा दो. तो नहीं नहीं नहीं, कम्युनिकेशन भी यूज करो और ड्रॉप भी यूज कर लो. तो फिर आ गया ना रोल इनका, एआई का, मशीन लर्निंग का आ गया रोल उसमें फिर, है ना. तो रिसर्च ऐड होती रहती है, ऐसे धीरे धीरे रिसर्च में चलता रहता है, उसका एडवांटेज मिलता रहता है. प्रैक्टिकली डीसी माइक्रोग्रिड देखा है? डीसी ग्रिड देखा कहीं? क्यों नहीं होते?
DC load, there's, we can say laptop, mobile charger, some light. Yes, in data center there is also load DC.
In simple home, if there is a PV bed and one storage, they will consider a simple DC microgrid.
Yes, yes, yes. You can use, if you have DC appliances, you can use. Yes. See, what is a data center? एक इन्फोसिस की बिल्डिंग है बहुत बड़ी, वो यदि अपना डीसी ग्रिड बना ले तो जो इसके पीसी है, पहले एसी लेते हैं, डीसी में एसएमपीएस है, ये है वो है, हाँ, 2 बार पावर कन्वर्शन करके वो यूज होता है. तो डाटा सेंटर में हम डीसी ग्रिड बनाते हैं. तो ऐसी जो टिपिकल लोड्स हैं, देयर वी कैन हैव लोकल डीसी ग्रिड्स.
तो वहाँ पर डबल लाइंस मतलब
मैंने नहीं देखी, मैंने पढ़ा है थियोरेटिकली आपकी तरह. नहीं नहीं होंगे, मुझे लगता है होंगे. हाँ,
2 लाइंस तो डालनी पड़ेगी, क्योंकि कॉमर्शियल बिल्डिंग है तो एसी लोड भी कुछ ना कुछ तो होगा. मतलब डेटा सेंटर भी है तो उसमें भी बिल्डिंग्स है जहाँ पे भी ऑफिस के एसी वगैरह ही.
हाँ, कुछ ना कुछ होगा.
Yes, sir, in our lab.
डीसी, अरे आपने वो नहीं देखे डीसी फ्रिज, डीसी एसी सारे नहीं, अलग अलग आ गए हैं, बड़े कॉस्टली हैं पर अभी हैं. फैन तो अवेलेबल है सब.
Sir, how we will do stability analysis in real life.
इन देयर.
Stability analysis of microgrid. How we will do it?
मैं इस फील्ड का नहीं हुई, टिपिकल पावर सिस्टम वाले से पूछना.
Nowadays they are using virtual inertia concept.
ये एफएफआर क्या बताया मैंने यार? स्टोरेज ही है वर्चुअल इनर्शिया, स्टोरेज का दूसरा नाम है वर्चुअल इनर्शिया. कैसे भी प्रोवाइड करना है आपको स्टोरेज. इनर्शिया क्या है? स्टोरेज तो है, काइनेटिक एनर्जी स्टोर हो रही है वहां पे. यहाँ पे आप फिजिकली उसको स्टोर कर रहे हैं, वहां भी फिजिकली स्टोर हो रही है, इधर भी. तो एनर्जी स्टोरेज का बड़ा काम है आज की डेट में.
There is, sir, one big question for research. Our government is decided to generate power more than 30 or 40% from renewable resources.
Yes, yes. We are generating 40% as on today.
But thing is that because of the new computing system side, there is less inertia. And whenever power is going to change, at that time, how to manage by conventional Because renewable energy sources, especially for PV system, their inertia is very low compared to conventional.
इनर्शिया आपको बाई करना पड़ेगा ना, किसी से तो पैसा दोगे ना इनर्शिया की, तो इनर्शिया एनर्जी स्टोरेज वालों को दोगे पैसा, या कटेल करके करोगे इसको, कहीं ना कहीं पैसा तो लगाना ही पड़ेगा उसको।
That means we have to give energy storage months.
यस, तो जब भी तो इतना इसमें आ रहा है आजकल, एनर्जी स्टोरेज कैसे करेंगे? एनर्जी स्टोरेज तो चाहिए आपको। माइक्रोग्रिड में तो स्पेशली नीड बैलेंसिंग, लोड बैलेंस कैसे करोगे? एनर्जी स्टोरेज के बिना तो कर ही नहीं सकते। मैंने इसलिए नहीं ज्यादा डिस्कस किया, मैंने कहा काफी लोगों ने पावर सिस्टम पे बताया होगा।
But there should be a challenge, sir. When you are going to generate 50% of 130 gigawatt, watt generation for renewable energy source, according to that, we have to have energy storage device. There should be big challenge. Manage this.
यस, नहीं उसमें से कितना है वो देखना पड़ेगा ना, किस लोड के लिए आप स्टोरेज लगाओगे, किसके लिए नहीं लगाओगे, वो डिपेंड है ना। तभी तो हम लोड शिफ्टिंग की बात कर रहे हैं ना, ये लोड को शिफ्ट करो, जितना उस पीरियड में हो जाए तो शिफ्ट कर दो। शिफ्टिंग आज की डेट में इसेंशियल है।
Okay. I think this session is already discussed. Many questions. Now, how I would like to thank sir.
थैंक यू वेरी मच।
Sir has given opportunity for us to deliver this nice topic, voltage and frequency control, or we can say.
नहीं, I'm not talking about microgrid, right?
Yeah.
But you see in microgrid, these type of power plants will be there.
Sir, this FDP is hybrid microgrid, sir. So hybrid microgrid is nothing but it is a combination of DC and AC microgrid. So sir, whatever talk about AC microgrid, so somewhat it is the part for hybrid microgrid. So thank you for this, sir. You have given a wonderful lecture for us. Thank you, all participants. Thank you, sir.